Alrighty, howdy folks. The next section is chapter 2, section 6. Uh, we'll, I, I want to say this is the last section in all these multiple cash flows thing. Okay, just a recap. First, we started with single cash flow. Then we did multiple cash flows in which first one was irregular, meaning you could deposit any amount of money at any time or take out any amount of money at any time and things like that. There was no rhyme or rhythm is how I have been putting it. And the one after that is a uniform series. Let's say you keep depositing every year certain amount of money. How much would you have in the future if you were to do that? So that was uniform series. And right after that, we looked at uh, a, a gradient series. After uniform, yeah, gradient, but that was an arithmetic gradient. What do I mean by that? The way the deposits kept increasing is, let's say you start with a G in year 2, the year after that is G plus G, that is 2G. And year after that, you increase it by another G, so making it 3G. So G, 2G, 3G, 4G, and so on, right? That is called an arithmetic increase because to get the subsequent one, you need to add something, right? However, this time we are going to do a multiple cash flow, but the gradient is a geometric series. What do I what do I mean by that? So let's look at this. The gradient series geometric. This figure, my hope is, explains clearly what we mean by that. Let's say we start with some A1 at t equals 1. The next year, the withdrawal in this case is A1 times 1 plus j. So A1 times 1 plus j. Okay, and after that, A1 times 1 plus j, the quantity square. So each time this is proportionately, it is increasing uh, not proportionately as a geometric series. I think geometric sequence. Cool. Um, Kind of like how we had a geometric series that looked like a plus ar square plus ar cube and so on. It's kind of like that. A1 times 1 plus j, A1 times 1 plus j square, and so on. So what would be the present and future values in such a distribution is what we are attempting to. Now, needless to say, can we apply the good old strategy even in this case? The answer is yes. What good old strategy, man? That strategy was, if you want to find a present value of each of these things, do one thing. Take every one of them and project back to 0. So A1 projected back to 0, A1 times 1 plus I to the 1 plus I to the negative 1. Then this one, the second one, would be A1 times 1 plus j times 1 plus I to the negative 2, right? We are pushing it back by 2 years, and so on. I hope you get the idea. A1 times 1 plus j is the quantity, this A1 times the quantity 1 plus j square times 1 plus I to the negative 3, like that. Okay, so that's what we do. And that's exactly what I'm saying here. And eventually, the very last one is a1 times 1 plus j to the n minus 1, but it needs to be pushed back by n years. So our factor is 1 plus I raised to negative n. All right. So the idea is, can we find the sum of this? If you feel up to it, can you challenge yourself to finding the sum of this one without me telling you? Give it a try. That's not a bad idea, just as a pure mathematical exercise. But if you don't want to, that's perfectly fine too. Cool. All right. So, uh, would this be bragging if I were to do this? I, I apologize if it is bragging. But when I saw this as I was preparing for this course, I said, dang, can I find this? Can I do this? And I had a bit of a struggle, I must admit, because this is 1 plus I to the negative 1, whereas this is 1 plus j times 1 plus I to the negative 2. Uh, uh-huh. I could have done that. Hmm. Well, sorry. I was lost in a thought. I think I could have recognized that this stupid thing is a geometric series with r equals 1 plus j times 1 plus I to the negative 1. As simple as that. Why didn't I think of that? Oof. Okay. All right. Anyways, I apologize. A1 times, I factored out a1 times 1 plus I, 1 plus j, the quantity to the negative 1. And when I did that, the inside stuff ended up being 1 plus j to the 1 times 1 plus I to the negative 1, 1 plus j the quantity square times 1 plus I to the negative 2. So the whole purpose, the whole idea is the powers that 1 plus j and 1 plus I are raised numerically to the same thing, even though one is positive and the other one is negative. So that kind of made stuff easy for me, I think. Okay, so let's pick back that stuff and try to figure out. However, in this, it ends up that there are two separate cases. When I equals j, what would be the formula? And when I is not equal to j, what would be the formula? Okay. What? Why is that? Well, look at this. When I is in fact equal to j, what happens to the stuff inside the square bracket? This 1 plus j, or we can call it 1 plus I, right? 1 plus I, the quantity raised to 1, times 1 plus I, the quantity raised to negative 1. Oh, it's the same quantity 1 plus I being raised to positive 1 times that's 1 plus I raised to negative 1. It's kind of like a to the 1 times a to the negative 1. What is that? Isn't that just 1? Right? 1 plus j, the quantity square, times 1 plus I to the negative 2. This becomes 1 a square times a to the negative 2. That is also 1. If we go all the way to the end, that is also something like a to the n times a to the negative 1, which is 1. So in the event I equals j, all these terms inside the square bracket just become 1 plus 1 plus 1 plus 1 plus 1. And how many of them? There are n number of them. How do I know there are n number of them? Look at this. The first one has a 1 plus j raised to a power of 1. The first one has 1. The second one has a power of 2. And which one should have a power of n? Stands to reason the nth one. So that's how I know there are n number of terms. Each one of them becomes 1. So 1 plus 1 plus 1, so on. If you add them n number of times, what should you get? What? Check this out. If you add 1 2 times, what do you get? 1 plus 1, 2. If you add 1 3 times, what do you get? 1 plus 1 plus 1, 3. Ah, now are you getting a hang of it? So if we add n number of times, we should get n. As simple as that, right? So in that case, the whole thing becomes fairly straightforward, and the formula becomes n times a sub 1 times 1 plus I, the quantity raised to negative 1. Cool? All right. When I is not equal to j, then what is the situation? Well, the stuff inside is a geometric series, clearly. because you have this and this one. So if you were to multiply the first term by 1 plus I, sorry, oh, I should show you this one. 1 plus j to the 1 times 1 plus I to the negative 1, and this is 1 plus j the quantity square times 1 plus I raised to negative 2. So each time we are multiplying by 1 plus j times 1 plus I to the negative 1. So that is the R. And that is what, and we already saw that the sum of a geometric series is a times r to the n minus 1 over r minus 1, with here a is the first term. We're looking at the stuff inside the square brackets, 1 plus j to the 1 times 1 plus I to the negative 1. So that's the one. And r is the same thing as a in this case. Okay, 1 plus j times 1 plus I to the negative 1. Cool. Armed with that piece of information, if we were to say P is this stuff that you see is what is outside of the square bracket. This guy. I just copied that. Now, for the stuff inside the square bracket, I'm applying this sum of the geometric series, which becomes 1 plus j to the n times 1 plus I to the negative n, right? R to the n. This stuff raised to, the whole thing is raised to n. So because these are multiplying, I need to raise each one of them to a power of n. 1 plus j to the n and 1 plus I to the negative n. That's what I have. Minus 1, right? R to the n minus 1. That's what you see here. Over r minus 1. 1 plus j times 1 plus I to the negative 1 minus 1. Cool. Oof. So this is the formula. But could we simplify the look of this? Yeah, check this out. Is this 1 plus I to the negative 1 the same as 1 over 1 plus I? And then would you agree that 1 plus I would be multiplying the denominator? So go ahead, multiply the denominator by 1 plus I. What happens? 1 plus I times 1 plus j times 1 plus I to the negative 1. Hey, that 1 plus I to the 1 plus I to the positive 1 and 1 plus I to the negative 1, they multiply to give you just 1. So all you are left with is 1 plus j minus, we need to multiply this also by 1 plus I, and you get 1 plus I. So all that is to say, the denominator becomes, I'm patient. Wow, I'm impressed. Now, as you can see, when I distribute this to the first term, I'm just left with 1 plus j. And if I distribute 1 plus I to the 1, I get 1 plus I. Cool. So that's a slight reduction in the complicated formula. But wait a minute. In the bottom, do I have 1 plus j minus 1 plus I? Can I not just simply, distribute the negative sign and write this as 1 plus j minus 1 plus minus 1 minus I? And so 1 and minus 1 add up to 0. And would I get j minus I? Yeah. That is nice. But then, could I rewrite this like this? 1 minus this quantity over I minus j. Basically, I'm multiplying both the top and the bottom by a negative 1. I can do that, right? I can multiply both the top and the bottom by a negative 1. And when I do that, this negative 1 becomes positive 1, and this becomes negative of this, and I'm writing this as 1 minus this. Okay. So this is the formula for the present value. This is the formula for the present value in the case of geometric gradient series. Cool? All right. So let's make this into a piecewise function. You remember piecewise function? Absolute value of x equals x if x is greater than or equal to 0, equals negative x if x is less than 0 stuff. It's like that. So the present value is, if I is not equal to j, this is the formula. If I does turn out to be equal to j, you get this. Cool. Now, why? Why do they have to look at them as special cases, as two separate cases? Couldn't we use this formula for I equals j case? What happens? Check this out. Would we have I minus j become I minus I, which is 0? Right? That's bad. So dividing by 0, it should go to infinity? Not quite. Check this out. 1 plus I to the n, that times 1 plus I to the negative n. That's what would happen if you have j equals I. So we have a to the n times a to the negative n, which is just 1. So on the top, we have 1 minus 1. So we have a 0 on the top and a 0 on the bottom in the event I equals j. So we have 0 over 0, which is undefined. Right? Now, does that ring a bell? When you try to do this, you get a 0 over 0. Do you remember what you did in calculus whenever you bumped into 0 over 0? For example, uh, x square minus 1 over x minus 1. Or maybe a better example would be, what is sine x over x if x is 0? Sine 0 over 0, that is 0 over 0. But then you can always talk about limit, right? Limit as x approaches 0 of sine x over x. So the truth is, if you were to do a limit as I approaches j, you cannot say I equals j. That's clearly undefined. But if as I approaches j or j approaches I, either way is fine. If you do that, take a limit of this one, guess what? You end up getting this exact same thing. Okay. As an exercise, if you wanted to do that just to challenge yourself, that would be wonderful. Otherwise, let's move on. Cool. For a geometric series of cash flow, the future value f, the good old thing, right? We know we have found a formula for the present value. You want to find a formula for the future value? Just take the present value, multiply that by 1 plus I, the quantity raised to n. But one thing I have to tell you though, be absolutely clear in your heads about which one is I and which one is j. Okay? I is the interest rate and j is the rate at which the deposits themselves are increasing, that factor by which they are increasing. Cool? So that is the difference. As long as you keep that in mind, all these calculations are fairly straightforward. Wait a minute. What did I say? Multiplying this by 1 plus I to the n gives us this formula. Is that true? Are you with me? If we multiply this p-value, I not equal to j case, is it true that we get this? The answer is yeah. Imagine multiplying this top by 1 plus I, the quantity raised to n. So distribute that. 1 plus I, the quantity raised to n is 1 plus I, the quantity raised to n, which is what you see here. But then 1 plus I, the quantity raised to n, times 1 plus j, quantity raised to n, times 1 plus I to the negative n. The first and the third term that are multiplying, they just become 1. A to the n times a to the negative n. Oh, so you would be left with 1 plus j, the quantity to the n, like I showed here, right? Now, don't say, hey, what happened? Shouldn't we multiply the denominator by 1 plus j? No, you don't. 1 plus I to the n? No, you don't, right? If I have 3/4, okay, if I have 3/4, and I multiply that by 2, should I multiply both the top 3 and the bottom 4 by 2? No, you just multiply the top. So when we multiply this fraction by 1 plus I to the n, you just use that 1 plus I to the n to multiply only the top terms, distribute it only to the top terms, not to the bottom. Okay? All right. And then what happens? This one, if we multiply by 1 plus I to the n, oh, simple, n times a1 times this quantity times 1 plus I to the n. Isn't that like in the form of a to the m times a to the n, which is a to the m plus n? So exactly. So that becomes 1 plus I to the negative 1 plus n, or negative 1 plus n we can write as n minus 1. So that's where this formula comes from. Cool. All right, let's look at a few problems. A famous high-volume calculus text generates royalties beginning with $60,000 in the first year and declining each year by 40% of the previous year due to used sales and competition. The author is on a 4-year cycle of revision. Determine the present worth of one complete cycle of royalties if the author's time value of money is 7%. Okay, one complete cycle of royalties. So the author writes a textbook and gets 60,000. The next year, he won't get 60,000. 60,000, we need to reduce that by 40%. What? We need to reduce that by 40%. How do you do that? So how much would he get if you reduce by 40%? Okay, let me make a slightly simpler problem. Okay. A jacket is $60 and you're getting 40% off. What is the price? What? The jacket is $60. You got a 40% discount. So now what is this price? Let's ignore the taxes. Oh, you said 40% of 60. So let me calculate 40% of 60. That is 24. And that is the discount. So from 60, I'll subtract this discount of $24. 60 minus 24, 36. Ta-da! Yes, you're absolutely right. But then, would you agree there is a much simpler way? That is, 40% is the discount, meaning you don't have to pay 40%. Without any discount, you should pay 100%, right? But with a discount of 40%, you don't need to pay 40%. So what percent should you pay? You should pay 100 minus 40, 60%. Cool? So what should you pay? You should pay 60%. Oh, 60% of what? $60. So 60% of 60, so is 36. So you didn't have to calculate 40% and then subtract from 60. Instead, you could just calculate 60% directly, and that's the amount you pay. And this, ladies and gentlemen, is precisely the same idea. He gets $60,000 the first year, and the next year he gets 40% of the previous year. So each year and declining each year by 40%. So he gets 60,000 times 60%, right? 36,000, and 36,000 times 60%, 0.6 is what you need to keep multiplying by. Okay. So this is a geometric series with A1 to be 60,000. J is it's coming down by 40%, so negative 0.4. I, interest rate, is 7% per annum, which is 0.07. The cycle has how many years? It's a 4-year cycle. First year and declining, blah, blah, 4-year cycle of revision. So n equals 4. Right? So if we do this, since I is not equal to j, that is true, right? Since I is not equal to j, we need to, what were we asked to find? This is present worth. Okay, we need to find a present worth of this. So we'll use that formula. A sub 1 times 1 minus 1 plus j to the n, blah, blah. It's a matter of plug and chug. Once you plug and chug and evaluate these quantities, you get $115,000, $115,037.72. Cool? All right. Should I give it tidbit? Do you know the Stewart Calculus textbook? Apparently that guy is a multi-millionaire because his textbook is sold in so many places. He passed away, but he's sold in so many places that he's a multi-millionaire apparently. So my point is, go ahead and start writing a textbook. Okay. Injecting a bit of humor, I suppose. Problem. On your child's first birthday, you open an account to fund her college education. You're a good boy. You deposit $2,000 to open the account. Each year on her birthday, you make another deposit, with each being 10% larger than the previous deposit. The account pays interest at 5% per year, compounded annually. So how much money is in the account immediately after the deposit on her 18th birthday? So this is also a geometric gradient series with A1 being 2000, J. Each year the deposits are increasing by a percentage, and that J is 10% or 0.1. Interest rate is 5%, so I is 0.05. 18th birthday, 18, and you want to find out how much money is in the account immediately after the deposit on her 18th birthday. So n is 18. F is what? Since I is not equal to j, we'll apply that formula, plug and chug, and turns out to be $52,410.42. Man, I cannot seem to read numbers. Okay, so that is this problem. So oh, this is the present. Yeah. Now let's bump it into the future by multiplying by 1 plus I to the n. And n is 18, plug and chug. We get 1. Whoa. So that's interesting. Just $2,000. And then you keep increasing it by just mere 10%. 2,000 times 1.1, 2,000 times 1.1 square, and so on. So if you do that, you end up accumulating $126,000 by the time the daughter reaches her 18th birthday. That is interesting. Cool. Let's look at another one. A boat is purchased by financing $50,000. The loan is to be paid for over a 5-year period with annual payments on a 15% compounding rate per year. Whoa, that's a lot, 15%. Each successive payment is scheduled to be 10% greater than the previous one. Determine the size of the smallest payment and the largest payment. Ooh, okay, that's interesting. Once again, this is a geometric series, a geometric gradient series, gradient geometric series, with P is 50,000, J is increasing, so 0.15. What? Oh no, the payment. I'm sorry. Payment is scheduled to be 10% greater, so J is 0.1 and I is 0.15. N is a 5-year period, so we got this. And what are they asking us? What is the smallest payment and what is the largest payment? What's up with that? Oh, if you recall the picture, we do A1, the year 1, A1 times J, A1 times 1 plus J the second year, right? So on. So the smallest payment is exactly the same as that A1. And the largest payment is something that we need to figure out. I'll show you a picture of it. I have it at the end. So basically, if we figure out what A1 is, which is the smallest payment, then we can figure out the other stuff effortlessly. Good. So A1 is what? And A5, the fifth one, what is that? Are the two questions we need to answer. Again, I is not equal to J. So we find the present value of this, right? The boat is purchased by financing 50,000. It is that 50,000 that we need to pay up. So P is 50,000. And we got this. Oh, I don't know. I should mention this, right? I cannot just go on, okay, plug and chug. P equals A1 times this one. But what we are invested is A1. What is A1? So, would you agree I need to multiply by the reciprocal of this on both sides in order to get A1? So that's exactly what I did. A1 equals P times the reciprocal of this is we are just flipping the top and the bottom, I minus J over all of this stuff. Now let's plug and chug. P is 50,000, blah, blah, and we get A1 to be $12,544.41. That is the first payment that you need to make. But understand that those payments are going to be increasing each year by 10%. So the largest payment, A5, what should it be? So here I have a picture to give us the idea. A1 is the one at t equals 1, and A1 times 1 plus j, A1 times 1 plus j square, and eventually at n, A1 times 1 plus j to the n minus 1, right? So what are we asking? We are asking our n to be 5. Cool. If n is 5, the payment there would be A1 times 1 plus j to the 5 minus 1. All we need to do is plug 5 for n in this nth payment. And if we do that, we get $18,366.28. So the very first payment was $12,544, and the very last payment is $18,366, and in between must have steadily increased by 10%. Cool. All right. Folks, that's it. Thank you.